Hello everyone. Today we will be learning an important relationship between radius of curvature and focal length for spherical mirrors. Now we have seen in my last video that focal length and radius of curvature is the distance of the center of curvature from the pole of the mirror. Now, the focal length or the focal point, what is it? Focal point is a particular point on the principal axis such that, let me explain it with the help of a diagram. If I draw a concave mirror, this being the principal axis, this is the pole P. If you consider a ray which is parallel to the principal axis is incident on a mirror, the rays which are parallel to the principal axis are called paraxial rays. These rays, after reflection, will pass through a point. This point is called the focus, and focus is exactly half of radius of curvature. Means it is exactly midway between half of the radius of curvature distance. So if this is the center C, this distance we know will be the radius of curvature. Now to establish the relation between the R and F, consider this paraxial rays which is after reflection passing through F. We will first draw the normal. In order to draw the normal, how to draw the normal in case of concave mirror? The principle is to draw one tangent to this line first. Draw a tangent here first. From the tangent you draw one normal. This normal will always pass through the center of curvature. Wherever I draw it, it will always pass through C. Now, according to the law of reflections, this will be the angle of incidence. So I will name this as theta, and this, according to law of reflection, this is angle of reflection, which both of them being equal, so denoted by theta. So this overall angle becomes 2 theta. Now if you see, if this one is theta, this must be also theta, as they are alternate angles. Similarly, in this case, now look at this portion. This overall angle is 2 theta. So this is 2 theta. This must be also 2 theta. Now, in order to establish relation, we also draw one perpendicular from here. Further, let me name this point as M, and I will draw one perpendicular. This is N. Now, the assumptions what we are going to make is that the point M is quite close to P. When this happens, the angles theta or 2 theta will be very small. So, what is our main assumptions? Assumption to establish the relation is that the point M and P are very close to each other. So when this happens, what will happen? The angles will be formed. So angles are small, right? Also, the length of MP is approximately equal to MN. Keep that in mind. Now let us say, from the triangle, it's a very simple derivation, no need to worry. From the triangle, triangle M N and C, M and C, you can see what can we write? We can write tan of theta almost equivalent to theta. Now why this equivalent? Because we are taking that M and P are very close, so angles are small. As angles are small, tan function of theta is almost equal to the theta itself. So based on this, we can write tan of theta would be perpendicular of hypotenuse by base. So perpendicular would be Mn. Oh, no, sorry. So it would be Mn by Cn, which you can write as Mn by Cp. Similarly, from triangle M N, tan of 2 theta equivalent to 2 theta equal to Mn by Fn. Now which is almost again equivalent to Mn by Fp. As we have said that these are all equal. This distance Mn and Fp will be almost same. These distances are. So actually so Cn will be equals to Cp also. I will write it here for you. So Cn equivalent to Cp and Fn equivalent to Fp, right? So now this is my equation 1, this is equation 2. So if I substitute this value of theta, in 2 theta, let's see what do I get. So 2 Mn by Cp equal to, sorry, yeah, theta is equals to Mn by Cp. So Mn by Cp equal to Mn by Fp. So now Mn get cancelled. I get here 2 by Cp equals to 1 by Fp, implies Cp is what now? Cp is, let me use another color to explain you this one. Cp is radius of curvature and F is focal length. Therefore 2 by R is equals to 1 by F. So we can write, taking reciprocal, F equals to R by 2. This is how we establish the relation between F equals to R by 2. Now again, let me explain you in short that we consider one paraxial ray. We consider one paraxial ray which is coming, which is the parallel to the principal axis after reflection is passed through the focus. This is actual definition of the focal length, that a focal point is a point on the principal axis such that any rays which is parallel to principal axis will pass through it, and any ray which originates from A after reflection will become the principal axis. This is actual definition of focal point. Now if you consider that this ray is very close to the principal axis, so we consider a ray which is a paraxial ray is close to the principal axis. After reflection, it passes through the focus. Now, as the ray is quite close to the principal axis, so some assumptions is that the angles will definitely will be small. So as the angles will be small, we can see that tan theta can be written as tan of theta can be written as tan of theta can be written as equivalent to theta, and tan of 2 theta can be written as equivalent to 2 theta, and so on. So from triangle MNC, what do I see? That perpendicular by this perpendicular is MN and CN. And again, MN by CN can be written as MN by CP, because here is our approximations. Our approximations are here. This is what we always consider. So similarly, then from triangle MNF, again we can take tan of 2 theta is equals to 2 theta equivalent to Mn by Fn, and then Mn by F. If you substitute each other, you get F equals to R by 2. That's it. This is how we establish the relation between R and F. Similarly, we can use for convex mirror also. When case convex mirror is a diverging mirror. So in case of convex mirror, the law exactly same thing will be followed.